copy this entire diagram. I put this picture up here to help illustrate a point that I would like to make about your periodic table. So it might be useful to have your periodic table just visible to you so that you can look at it. Now, our discussion today is going to revolve around something called valence electrons. Well, that was interesting. I think it would be worth your while to write down what a valence electron is first, and then I'll talk about this picture that I've got up on the screen here. Now, up until now, I've simply asked you how many electrons does something have. I cared where they were, but I never differentiated with a name between the electrons and, say, the first and the second energy level. So earlier today, when people came up and drew pictures of that carbon atom, what we were really drawing were 2 electrons on the first energy level, 4 on the second, and those 4 were the valence electrons. So a valence electron is an electron in the outermost energy level, and the key is those are the ones that could potentially participate in a chemical reaction. Now, generally, it is only valence electrons that participate in reactions. They're the farthest away from the nucleus, so they're held the least tightly. It doesn't mean that every single valence electron participates in a reaction, but if something were to participate, it is very probably one of those electrons. So that's what a valence electron is. And what I wanted to illustrate to you first is that there is a quick and easy way to know how many valence electrons something has. If you look at your own periodic table, you'll recognize that I've basically replicated it here with some slight differences. Here's family number 1, here's family number 2, nothing is different there. On your periodic table, this is family 13, 14, 15, 16, 17, and 18. You'll notice I skipped over the whole transition metal chunk in the middle because they don't follow the rules quite as nicely as the other elements do. The idea is that based on the family something is in, you know how many valence electrons it has. So, something that you might want to note is that family, the family that you're in, helps determine the number of valence electrons. So just as an illustration, I wanted to show you that everything in family number 1 has 1 valence electron. Everything in family number 2 has 2 valence electrons. Everything that is in family 13 has 3. Family 14 has 4. Family 15, 5. 16, 6. 17, 7. 18, 8. And if you look at the periodic table, kind of the same pattern emerges on each row. On every row, you have something that has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Then you start over again. 1, 2, 3, 4, 5, 6, 7, 8. So there's a pattern. There's a pattern because everything in the same family has the same number of valence electrons. But as you go across a period, every time you move one step to the right, the number of valence electrons goes up by 1. So those are a couple of shortcut tricks for knowing how many valence electrons something has. Now, you could always draw or figure out valence electrons just by counting electrons. So I'm going to use hydrogen and lithium as examples to show you how I know that they have 1 valence electron. An atom of hydrogen has In its nucleus, 1 proton. And on the first energy level, 1 electron. And that's all that it has. Hydrogen has no neutrons. It's the only one where your answer would be 0 for neutrons. Lithium, in its nucleus, because it's number 3, would have 3 protons, 4 neutrons normally, and it would have 3 electrons, 2 in the first level and 1 in the second level. Now, even though hydrogen and lithium have a different number of total electrons, they have the same number of valence electrons, because valence electrons are whatever you find in the outermost level. And so even though their overall structure is not identical, what is in their valence level is. So you could figure out the number of valence electrons either by using the family and period it's found in the periodic table, or by actually figuring out the structure the way we had drawn atoms before. Does anyone have any questions about what a valence electron is, or how I would figure out how many there are? So you'll see the title at the top of this page is the octet rule, and I'm going to pick out a few elements to use as an example to illustrate the octet rule. I'm going to use neon, fluorine, and sodium, and I'm just going to make a new screen so I have a bit more space to work with. So those are the ones that I'm going to choose, and I'll redraw them in case you don't have a chance to draw them here. So, what is the octet rule? The octet rule actually has a bad name because it sort of insinuates that 8 is the magic number, and that's the case most of the time except for a few exceptions. So, the octet rule is telling us something about the number 8, and for most atoms, that's the key. So before I write out the definition of the octet rule, I'd like to use my illustrative example. I was going to talk about elements that I found in families 1, 17, and 18, but they weren't all in the same period. So in period number 2, I had fluorine and neon, and in period 3, sodium. So I'm just trying to represent those where they actually are on the periodic table. Now, either by adding up the total number of electrons or by using the family shortcut that I showed you, I should be able to determine that neon has 8 valence electrons, that fluorine has 7, and that sodium has 1. Now, we mentioned it before, so could someone remind me what family 18 is called? That last family on the periodic table. Yes. Noble gases. And they're not called noble gases for nothing. They're called noble gases in part because they have the best configuration. And so noble seems to indicate best or highest or whatever. Noble gases, if you look, with the exception of helium, and that'll be an exception I'll mention later on, all have 8 valence electrons. Noble gases have what we would refer to as the maximum number of valence electrons. So however many levels they have the maximum number of electrons that that level could hold. Because they have the maximum number of valence electrons, they are very non-reactive. They don't need any more electrons. They have the perfect number already. And so it is unlikely for a noble gas to react with something else because its electrons are already maxed out. Now we'll talk about fluorine first. If you look at fluorine, it is very visibly one electron short of being like a noble gas. Fluorine is very reactive. And the reason it's very reactive is because it really, really wants that one extra electron so that it could be like the noble gas that it's closest to. It's not going to become neon. It would have to acquire more protons to do that as well. But it's going to try to achieve the same electron configuration. That's its goal. So all atoms are trying to be like the noble gas that they are closest to in terms of electrons. Protons and neutrons that are in the nucleus, those are really hard to change. But electrons, because they're orbiting around, those can change places. Now for fluorine, it's easy to see that if I added one more electron, now I have 8. For sodium, it's a little bit less clear, and so I'm going to draw the whole picture. In sodium's nucleus, I would have 11 protons, 12 neutrons. I would have 11 electrons to start with. So, sodium has one valence electron, which I've represented there with the one red dot. Now, sodium could, I guess, get 7 more electrons, but 7 is a lot. That would be really, really difficult. It would be much easier for sodium to just get rid of that one electron. As soon as sodium gets rid of that electron, well, now it doesn't have any need for this outer energy level anymore. And its second level becomes its valence electrons. There are already 8 electrons there, and so for metals like sodium, instead of trying to gain 6 or 7 electrons to make up 8, they will lose their outer energy level so that the next level down can become the valence level. So for a metal like sodium, it will lose electrons to make the next level the valence level. That's the idea. So for a nonmetal like fluorine, it will just fill up its existing electron energy levels. For a metal like sodium, it will just drop electrons and get rid of its outer energy level. So back to the octet rule. The octet rule is really saying that in most cases, atoms are trying to achieve 8 valence electrons. That is their goal. Whether it's by gaining electrons in your existing energy levels or losing electrons and getting rid of a level altogether. There would be some exceptions here. Hydrogen and helium are the big ones because they don't even have an energy level that could hold 8 electrons. Hydrogen and helium are in the first period on the periodic table. They only have one level of electrons, it's the first one, and the most that it could ever hold is 2 electrons. So for those 2 elements, 8 is not their goal. Just so that we're clear, hydrogen, even though it could gain or lose 1 electron, most of the time hydrogen loses 1 electron to have 0 electrons. Helium only has 2 electrons. So those 2 elements are not going to get 8 total electrons. Now some other exceptions would be the first few metals that are in period number 2. For example, lithium and beryllium. Lithium and beryllium have that second energy level, so they could theoretically have 8. But lithium would have to gain 7 electrons, beryllium would have to gain 6 electrons, and that's not very realistic. So those two atoms in particular, they are not going to have 8 valence electrons. They will both end up having 2 valence electrons, so that their first energy level is totally full and the second one disappears. Now, I'm not going to mention boron because it's weird and it doesn't follow any sort of good rule. And I'm not going to ask you to use boron frequently. Boron, for whatever reason, only needs 6 electrons to fill up its valence shell. It's very weird. So we are not going to use boron at all really in examples here. Later, if you take Chem 20 and you talk about how bonds are formed, you might hear about boron. So I'm just mentioning to you, it doesn't follow the rules, but we're not going to use it very much. Does anybody have any questions that they would like to ask?